Hey y'all, welcome back. Sammy here. I'm looking to do some more LeetCode problems. Trying to do them in order. So yesterday we did number one, two sum. Number two is add two numbers. It's a medium difficulty problem. We're dealing with linked lists. And so you're given two non-empty linked lists representing two non-negative integers. The digits are stored in reverse order and each of their nodes contains a single digit. Add the two numbers and return the sum as a linked list. You may assume the two numbers do not contain any leading zeros except the number zero itself, right? So for example, if I kind of just go out and explain the intuition here, right? The example number one basically says we have a linked list L1, right? And we have linked list L2. And L1 is basically 2, 4, 3, and linked list 2 is 5, 6, 4. And the problem states that the expected output should be 7, 0, 8. So L3 is our result or our output, and it's supposed to be 708 for this problem, right? So to better understand this, let me just explain what's going on here. So this linked list one, right, each made up of the different list nodes, each representing a digit. So linked list one, L1, actually represents the number 342. And linked list two actually represents the number 465, right? So this is like what it's saying when it says that the list nodes are containing the digits of a number in reverse order, right? So this is how we would see it as like humans, right? Like that's the way. So if I want to add these two numbers, I mean, we all know how to add. We'll start at the units, at this first unit place, at the single units place. So 2 plus 5, right, is 7. 4 plus 6 is 10, right? So we place the 0 here, and we carry the 1. And 3 plus 4 is 7, plus 1 is 8, right? So we get the answer 807, which we can confirm is actually the same as what they want us to return because the output is just 807 in reverse order, which is 708. Now, keeping this in mind, you might wonder like, hey, why do they give us these like linked lists in with the digits in reverse order? And it actually makes it easier for us because if we do like normal addition, we'll see that we start at the single units place and then we go left, right? And as we add numbers, if we got to carry anything, we move it, carry it to the left just like we did with the 10. We put the 0 here and we carry the 1. Same deal. So this actually makes it easier because we have, the reference to the head of each linked list to be the units place, right? Which is the same over here. So it's actually to our advantage and it makes it a little easier for us to actually solve this. So there's actually, two very important expressions or kind of like things we want to keep in mind. And the first thing is obviously the fact that if we just scroll down here, we have this notion of carrying a bit and then storing a bit, right? So we can't actually like for this example right here, right? Or let me give you another example. If I just write this right down here, for example, if we do 5 plus 7, right, that equals 12. We can't store 12 into a node, right? We can't do that, right? What we need to do is we need to say the node can store the digit 2, but we need to carry the 1, right? So that's something important to keep in mind, and I'll just show you what we can do. So we can actually, what we'll do is we'll actually create a temporary list node, right? L3. This is going to be what we're going to be returning, as our final answer, and we'll just initialize it to a dummy node equal to 0. We'll also use another temp head. We'll use another node, list node temp head, and we'll assign that to L3. And this will basically allow us to hold the reference to L3. And we can modify L3 as we, run through our algorithm. So that's the main intuition. So let me just erase this and let me explain what we need to do. So another two expressions that we want to keep in mind is that what we want to store in each list node has to be broken down. And I'll explain what I mean. So if we look at, for example, the same example one as shown on LeetCode. Let's say we're, for example, looking at this, right? The 10th place, right? Where 6 plus 4 equals 10, right? So let's start off by saying, hey, current val, right? That will be equal to L1.val plus L2.val plus a carry, okay? So outside our main loop, we're going to need this variable carry, right? We'll initialize it to 0 just for the beginning, right? So we've got this current val by getting L1 val plus L2.val plus carry. Now we need to break this current val into possibly not every iteration, right? Maybe we have 1 plus 3 where it's just 4. We don't need to carry, right? But for example, in this 4 plus 6 equals 10, we put the 0 in the node and we carry the 1 over to our hundredths place, for example. So the way we can do this is we can compute the carry by saying the carry will equal the current val divided by 10. So this is actually the expression that will tell us that, hey, the carry, this is what the carry is going to be. And I'll show you how that works. If, for example, if I say, 12 divided by 10, that gives us 1 because 10 goes into 12 once, right? If we do with a remainder of 2, right? So if we do 12 mod 10, right, the modulus operator gives us the remainder. So that means that 10 goes in 12 once with 2 left over, remainder of 2, right? So this will be equal to 2. And I apologize that you can't see that. I'll just write that up here. 12 mod 10 equals 2, right? So these are two things we want to make sure we keep in mind because they will be very necessary in solving this and keeping everything organized in terms of what we need to carry, what we need to place in our list node, right? So if we come down here, we've got the carry, and now we want to compute the digit that we want to store, right? So we'll create a variable in the loop, digit, and we'll say that is equal to current val mod 10. So there's a difference, right? The dividing by 10, the current val divided by 10 will give us the carry. Current val mod 10 will give us the rightmost digit or the remainder that we want to store as a digit in the specific list node, right? So once we have this information, we can actually continue the algorithm, right? We're looping through, we're traversing L1 and L2 as long as they're not null, right? So as long as they're not, they're non-empty, and we compute this set of information. And what we can do is we can say L3 dot next, right, equal a new node, and we will store in here the digit. And the next thing we can do is pretty much just advance. We can just advance pretty much. Just give me 1 second here. Yeah, so we can basically now advance all the pointers, so L3, L2, L1 to the next node. And this line right here is basically building our output, right? Where we have L3, we have saved the head of L3 in the temp head, right? So we'll use that later. I'll explain how that makes it easier for us. But L3.next equals new node, L3.next equals new node. So we're just building, linked list 3 as our output through this algorithm, right? And so this is basically the gist of it. However, there will come a point, actually it's very probable, that possibly L1 is not the same size or length of L2. Maybe L1 is shorter than L2, maybe L2 is shorter than L1, or vice versa, whatever, right? So we got to take care of that. So the way we can actually handle that error is we can say that if we can have two cases actually. We can have case 1 being L1 not equal to null and L2 is equal to null, right? We can have case 2 where it's the opposite. We can say we can say L1 is equal to null and L2 is not equal to null, right? So these are two cases we can have, and the way we handle it is not any different. It's really pretty much the same algorithm that we are doing up here. I'll kind of highlight this all in white if I can make a cloud around this kind of, and I'll explain what we do. The only difference is a very minor difference in each of these cases, right? So we'll actually do the same algorithm where we'll be computing the current value, we'll be computing the carry, we'll be computing the digit. But the only difference is because L1 is not null and L2 is not null, in case 1, the current val, so I'll just say current val, that will be computed as the L1.val plus the carry. Because obviously L2 is null, we can't use it. We're only taking care of what's left in L1, right? So current val is equal to L1.val plus the carry. We'll compute the carry, we'll compute the digit, and we'll do the same thing. We'll set L3.next to a node, new node, and we'll place the digit in there. And the other change is we will be incrementing L3, L1 to next. No L2 because we're not dealing with L2, right? And so this is this, sorry about that, that's a bad rectangle, all the same for case 2. Same algorithm for case 2. Except we don't have L1 here, we have L2. L2 is non-empty, L1 is empty. So the current val will be computed as L2.val plus the carry. We'll compute the carry again, just like before, and the digit. And we'll set L3.next equal to a new node. L3 will equal a new node, digit, right? That's what we're storing. And instead of incrementing L3 and L1, we're going to increment L3 and L2 to the next, right? So this is pretty much the main intuition or the algorithm behind this, taking care of the edge cases and computing the sum for each units placed, carrying over the bit, storing the digit, and moving on. Now, at the end, there might be a possibility that at the end of these two loops, where case 1 and case 2, we might have a carry, right? There might be a carry that we have not accounted for, right? If the carry is 0, which means there's no carry, right? For example, if we do in the same example, for example, if we look at the ones place in our problem right here, if I could just highlight that for you guys right here, 2 plus 5 equals 7. So we don't have a carry, we don't have to worry about that. But let's say at the end of our algorithm, we do have a carry. That means that we'll say that that basically means that if carry at the end is not equal to 0, right? Because we don't want any leading zeros like it said in the problem, right? Except if the digit is a 0, but we don't want any other leading zeros, right? So if carry is not equal to 0, we'll just set L3.next to a new node, and we'll place the carry as a digit. And that will be the end of our algorithm. So we'll go ahead and code this out. I'm thinking of doing this in C# today instead of Java, just changing it up. So yeah, let's go ahead and do that now. All right, so first we're gonna need the list node that we're gonna return. So the linked list that we're gonna return is L3. We'll just initialize it to temporarily 0. This is where I'm gonna create this temp head to just have a reference to L3, so we can actually modify L3 without having to worry too much about screwing the rest of the the rest of the data structure in memory. We'll just use temp head to point to L3 so we can always return it. At the end, we'll be doing return temp head dot next, and that's exactly why I'm doing this. At the end, we can just do temp head dot next because temp head currently is 0, which is not part of the answer, but dot next will be the linked list that we want to return. So now that I have that, we'll loop through L1 and L2 as long as they're not null. So L1 not equal to null, L2 not equal to null. And what we'll do is we do need another variable out here, carry, like I said, to keep track of the different carries. And we can say that the carry, actually, before we do that, sorry, the current value that we need is going to be equal to L1.val plus L2.val plus the carry. Now we need to bisect or kind of like, break down the current value into the digit, like I said, that we need to store in the node and the carry. God forbid if there's a carry, right? So we can do that in the following way. You can say carry equals to the current value divided by 10. We'll say int digit equals current value mod 10. So now we've just broken down our current value into the digit bit, and the carry bit. And we say L3.next. So this is how we build our answer out, right? Our result, the linked list L3, will set L3.next equal to a new node, and this will store the digit. And simply we just increment or advance each pointer to the next, and voila, that is it. Now, this is the case where we deal if, for example, L1 is non-empty, but L2 is empty. So we'll say while L1 is not equal to null, we'll repeat the same process, right? In current val equals L1.val plus the carry. The carry equals the current value divided by 10. The digit will equal the current value mod 10. And we'll advance L3. Sorry, before we advance, we need to set L3.next equal to a new list node. Yeah, list node. I think I misspelled it here as well. List node. And we'll place the digit in here, and we'll simply just increment or advance L3 pointer and L1 pointer. Okay, now we got to do the same for L2. So while L2 is not equal to null, and we'll compute the same data, current value equals L2.val plus the carry. The carry equals the current value divided by 10. The digit is equal to current value mod 10. We'll set L3.next equal to a new list node of digit. Store the digit in the node. We'll advance the L3 pointer, and we'll advance the L2 pointer. Okay, and the last thing we need to take care of is if we have any leftover carries, right? So if carry does not equal to 0, right, that means we do have a carry. If it equals 0, we don't care. We don't have to do anything. We don't want any, like it mentions here, we don't want any, the answer shouldn't, you may assume that the numbers do not contain any leading zeros. And same here, we don't have any, leading zeros on the output. Except for example 2, that is actually the answer. So, that's fine, but we don't want any leading zeros in our answer, right? So only if the carry is not equal to 0, what we can do is we'll say L3.next equals new list node, and we'll pass in the carry. And that should be the end of our algorithm. This is done in C#. Let's give it a run, see if it's working. Okay, accepted. Case 1 is correct. Case 2 is good, and case 3 is good as well. We'll go for the submit, see how we did. Okay, runtime 85 milliseconds. It beats about 73% of users coding in C#. Our memory is 49.26 megabytes, and it beats about 85% of users using C#. Guys, thank you for joining me. I hope you learned a little bit. I'll be posting probably LeetCode number 3 as well, working through these, trying to prepare for interviews. But yeah, if you guys have any questions, comment, and subscribe. Let me know. Thanks for watching. Take care.